Hello, everyone. Welcome to monthly AI Lithuania meetup. So today we have two interesting topics. So today we talk about speech recognition and sea traffic anomaly detection. Before that, I want to introduce myself. My name is Davidas Matačiūnas. I'm data scientist at IBM and a board member and organizer of Lithuania AI Association meetups. So if you want to participate as a speaker in our meetup or just know more information about that, you can always write me on LinkedIn page. Okay, so today's agenda. So I want to introduce a couple of community updates. Then we have two presentations by Julius Venskus and Donatas Tamašauskas. So Julius talks about semi-supervised and unsupervised machine learning methods for sea traffic anomaly detection. And then Donatas talks about speech recognition for small languages. And after these two talks, we have Q&A session. Then you can ask the question related to these topics for speakers. Okay, so community updates. I want to congratulate new elected Lithuania Association board. We have 5 members from previous board and 2 newly elected members, so me and Ruslanas, and also have Dovydas as our president. So second news, we have 2 new companies, which is join our association. So it's Biometric Design, which is doing protein structure with artificial intelligence, and Scorify, which help business to better understand their client using machine learning, econometrics, and artificial intelligence. So the last news we have, after a long time, we have participated in the live conference, which is called PyCon Lithuania 21. So me and Jeff presented topics about artificial intelligence. So I'm talking about how to fine-tune large NLP model, and Jeff talks about causal inference and experiments. So this is all the news from association. So maybe we should start with our first talk. So I want to introduce you Julius Venskus, software development team lead of Flinkfolk. So Julius today talk about semi-supervised and unsupervised machine learning methods for sea traffic anomaly detection. So Julius, if you are ready, I stop sharing my screen and you can start.
Okay. So I hope you see my screen. Okay. Hello, everyone. So warm greetings from coast of Baltic Sea. I'm here in Klaipėda. And of course, I'm happy to introduce my doctoral research that I did in Vilnius University. So a little bit about myself. I'm software development team lead at Flinkfolk that was just acquired by Valid. Of course, and like addition, I have our lectures at Klaipėda University and Vilnius University. So on today, I will introduce semi-supervised and unsupervised machine learning methods for sea traffic anomaly detection. That was research was done during my PhD research years. Okay, let's go. Yeah, what kind of motivation was behind of this research? So actually, that 90% of the cargo in the Europe is transported by sea, and of course, in such a huge traffic, it happens a lot of accidents, different dangerous situation. And in order to improve maritime situation awareness, North Atlantic Treaty decide to monitor better sea traffic and see what's is changing and what's happening in the sea. So that research is done under understanding of maritime situation awareness. So just what the what exists in traffic exists in the area, and that anomaly is one of the parts to see what's happening with such a traffic in the sea. Of course, current detection algorithms is not sufficient. That should be improved, especially when we're talking about unlabeled data and vast amount of unlabeled data. And one other thing that was missing, that is improvement of anomalous trajectory detection. Yeah, so a little bit clarification, what is the anomaly in this topic. Yeah, usually I follow Portnoy definition that as anomalies like detection approaches for build models of normal data and then attempt to detect deviations from the normal model in observed data. So actually, all base research is done is just creating a model that could represent a current sea traffic and detect events that are actually deviating from such a model. Yeah, and usually in the sea anomaly, the term this term is used interchangeably and with abnormal, normal traffic, anomalous traffic. And usually we in the sea we understand like vessel, ship deviation from lanes, navigational routes, trajectory, speed, or another changes of another traffic parameters. So research object was like detection of marine traffic anomalies in its data, and actually the goal to improve that anomaly detection. Yeah, a little bit about workflow of this research. Of course, one of the important part is data collection. It's a pointer. It's a data collection. And in research, I used two types of data. One was labeled, another was unlabeled, just to compare and look for methods that could detect anomalies in unlabeled data. Of course, data research, and we split data sets to labeled and not labeled. And for some investigation to check that unlabeled methods work, we use some unsupervised method to label unlabeled data in order to test a method that requires to have unlabeled data set. Yeah, a little bit what kind of approaches are used in anomaly detection in sea traffic. So usually in research, it's observed that it's two types of anomaly detection. One is a point-based, or sometimes called density. Just it based looked on how often in particular location, based on the coordinates, the vessel, let's say, sailed, and how dense the traffic was in particular area. In another approach is trajectory-based approach, and usually, and especially in my research, I use special temporal data analysis approach when I look to the data as special temporal data, and use and assume that data changes not only in a space but in a time too. Yeah, one of the important part, as usually in data science, is the data preparation. But let's talk a little bit what kind of data it is. Those for my research, I use automatic identification system data. So actually, each ship, vessel, or rescue helicopter sends his navigational data that consists from the location, speed, navigational status. All the data are sent to AIS base station, and that data are monitored by different vessel traffic services. And that data was collected during time period and was used to analyze traffic data. Yeah, my research use 3 types of data sets. One data set in the Klaipėda area, another in Fehmarn Belt area, just on the coast of Germany and Denmark. It used 2 different data sets. Was used because of it has total different traffic intensity, and it was one of the goals was to investigate how different algorithms behaves in smaller data sets and bigger data sets. Of course, the big role played meteorological data that was also collected on the same time period. Yeah, and with the data. So what is the preparation for the data? Okay, set collection, data are structured by individual vessels. So we have multiple vessels in the dataset. We have more as 5,000 individual vessels, different ships, boats, helicopters, military ships, etc. Of course, cleaning data as usual, duplicate, noisy data, down sampling, just to work with some data intervals. Of course, as usual in the real world dataset, we have a lot of missing values in dataset. So I used some missing values imputation methods to fill that gaps. Of course, feature engineering, and for and of course dataset was imbalanced, and I used balancing technique. It's called synthetic minority of sampling technique. And of course, the last one, missing vessel type imputation, that not all vessels set here, they type in IS device, so almost 4% is missing. Yeah, so as I mentioned, 4% of the data is without vessel type. And vessel type is very important parameter in the vessel traffic. Based on that, in the picture on the right side, each vessel type has colored with different color. It even visible with naked eye that each vessel leaves different paths in the sea. So actually, what's visible is that Fehmarn Belt sea area, and in red is marked as tankers, passengers in pink color, or fishing in blue color. So you actually even it's easier to observe that it has totally different traffic pattern. Yeah, so how to deal with that for 4% of missing vessel type data? So I have created multi-stacked, multivariate LSTM network that was learned on available vessel traffic that had a vessel type. And later on, I use the same train network to classify that missing data. I use the data from classifier to input missing values. Of course, we have like a final data set, and we have multiple vessel types, and is grouped by vessel types. In previous research, it was found that it's better to perform anomaly detection based on vessel types, because of course they using different pattern for moving around the area. Okay, so the first research was to see semi-supervised point-based vessel traffic anomaly. Here I have created a new method based by fusion of SOM method and virtual pheromone. The main idea is behind that all traffic is clustered with help of self-organized map that are clustered in some clusters. Each cluster has a unique number of how many vessels was arrived in that area, and we set a visual pheromone. That's like it's from the ant world, where you can understand the route of ants. The same concept was applied here. So each vessel coming to each cluster leaves a virtual pheromone path, and we can see ways more often traffic is happening. And of course, here we have like additional feature like pheromone evaporation, that during some over the time on some constant, we minimize the values of visual pheromone. And if traffic are constantly going in the same cluster, it always has same level of visual pheromone. But if in this area the traffic disappears, doesn't happen for some reason, it lowers. So we have like some threshold for that virtual pheromone. We calibrate that pheromone on label data, and we know that on some level of pheromone, if it is higher of particular level, we treat as a normal traffic, and if it is lower some level, we classify it as anomaly. A little bit another method. It's created similar approach that clustering is done on the same self-organizing map. So again, we have clusters, but all the clusters are additionally analyzed with Gaussian mixture modeling. So for each cluster, we create like additional Gaussian distribution model, and we are hello, can you hear me?
Yeah, we can hear you.
Yeah, apologies, some connection interrupted. Yeah, I hope you heard everything. Yeah, okay, let's go further. So, okay. After two methods was analyzed, I moved to a supervised part of anomaly detection. That was my main goal, to create an unsupervised method. Okay, so what I did here. So first thing, I decided to do a prediction of most likelihood vessel position over the time. So, and again, multi-layer, multi-stacked LSTM autoencoder was created. That input for that multi-autoencoder was, let's say, older locations, older navigational vectors that consist not only for the location, but with speed, speed, direction, weather, and all another data. I just compress it to a encoded latent representation. And later on, the coder decompressed it to a upcoming to a future steps coordinates of the vessels that will be over certain time. So first layer like input current location of the vessel. So actually the multiple locations, like in my dissertation, I use 50 previous locations. I predict upcoming 50 locations of the vessel. And for this type of model, I use MAIE loss function. That's pretty ordinary. But further to detect anomaly, that okay, we have like a future location, but it is anomalous location or is good location. For that, I decided to create 2 additional LSTM autoencoders to train it. So I have created 2 additional one. It's one upper bound model and lower bound model. Both of that model was trained with different loss functions. One of that loss function was used ReLU function, but with positive, that you took only positive error. And for lower bound, I use errors only with negative part of the error. And all 3 models was trained to reach confidence level of 95%. Apologies, prediction region. And in order to find such a prediction level, I use iterative approach. I was rising on some particular constant that was increasing an influence of each of special part of loss function. So in this case, if it is upper model, I increasing positive part of the error influence to a loss function. Is this lower lower bound? I using negative errors. Yeah, and that's why was I created this approach. Yeah, and of course the last one approach that I use more statistical approach. That I was training 100 LSTM autoencoders, but before training, I used while bootstrapping technique. That each training data I was mixing with multivariate normal random variables, like adding noise to a data. And that all models was trained on that artificially created noise. Actually, what I did here, I moved all traffic data with some unknown distribution to a known distribution that is actually a normal distribution. And later, all that models, I was able to use them to calculate based on the Fisher distribution to calculate a prediction region. Okay, well, a little bit about experiments. Experiments are, as always, I believe you know, that was created on TensorFlow, Keras, use some Minisom or Sklearn, a lot of Python-based libraries. Okay, the results of the prediction region learning. So the first part, each vessel type was trained separately. So we have like a data for vessel type, and we see that biggest error has vessels like towing, like diving or port tender that is much bigger errors. During the learning of prediction region, when I was growing, when the lambda parameter was increased, we see that PSP is a parameter to evaluate an anomaly. So we see that it's actually we're rising. That it means that we're reaching a defined 95%, and of course, its additional error was evaluated for that. Okay, and of course, I got results when I was comparing on validation and test data. So the errors pretty small ones that actually I was able to reach goal. And for vessels like port tender, it was a bigger difference. Like if goal was to reach 95 of normal data, it was able to reach only 48. Okay, so what is the results here? So we have, like example, some cases that are classified as normal. In the green line, here we see like vessel positions over the time. In cyan color, usually follows the same lanes as all other vessels do. And like black triangle, and see that actual vessel position is inside of this prediction region, and we can classify this traffic as a normal. But in cases of abnormal traffic, for example, we have like first case like a sharp connection sharp direction change. We see that so that actual location of the vessels is outside of Okay, the same test was performed on LSTM while bootstrapping method, and we see that even for data that has sufficient data points, we have pretty good accuracy. So we're reaching designated level of 95%. And of course, it is vessels that has much less data. We cannot reach designated later, and actually we see that that model cannot be learned on such small amount of data. In this case, if we had in machine learning approach, we had square prediction regions. In while bootstrapping, we have ellipse prediction regions that actually is more accurate. So we cover bigger area. And of course, again, we see normal cases. The same vessel is inside of 95% of vessels that usually fall under this region. And of course, the same cases, but use another method. We see that prediction regions are in prediction regions doesn't cover real positions of the vessels. So in this case, the traffic is classified as anomalous. Okay. What's the results? So all methods was comparing, and fortunately, it's a huge table, a lot of data. But if to be short, I observed that data with that method that based on the SOM that with Gaussian mixture module and with Pheromone, has pretty good, pretty high, low value of false negatives. So it was decided to analyze what kind of false negative it is, and just to understand what kind of algorithm, which type of traffic detects better. And we see in this picture that the traffic, vessel traffic trajectories was clustered. That was detected as anomalous by LSTM approach techniques against SOM-based techniques. And we see that trajectories that are like a sharp maneuver, that is in the red color, you see much better, or in blue color we have stopping line, it's much higher. That means that LSTM-based models that works on the shape of the trajectory detects anomaly more wider, can anomaly much more anomalous cases. Yeah, and what conclusion do we have? So based on that results, so we see that some pheromone method detects anomalies more accurately on smaller data sets. So some Gauss mixture model more accurately detects anomalies on the largest data set compared to a pheromone method. And research suggests, of course, appropriate best parameters such as some grid size, neighborhood function, etc. Yeah, and of course, both LSTM methods can be used for to detect marine traffic anomalies. The LSTM, while bootstrapping, we are unable to learn on smaller data sets, but the LSTM prediction region method was able to do so, but on narrower forecast regions. And of course, to fill the missing ship type values, LSTM multilayer classification method was developed, which allowed to fill in and use more that additional 4% of the data. Comparing to anomalous trajectories, it was observed that LSTM can detect anomalous trajectory forms as on sharp maneuver and stopping maneuver. Okay, that's all from my side. Thank you.
Yeah, thank you very much, Julius. So if you have any question for Julius, so it will be after Donata's talk. So, and then we, if you can stop sharing your screen.
Yeah, 1 second, I'm doing right now. 1 second.
Thank you.
Apologies, a little bit froze. Yeah, it's funny, but I have frozen. I need to kill this application.
Okay, let's try. Okay, so thank you, Julius. And we have our other speaker, our second speaker. It's Donatas Tamašauskas, CTO and co-founder of Oxus AI. And today, Donatas present us a topic, very interesting, how to use speech recognition for small languages. So Donata, if you're ready, I stop sharing my screen and you can start.
Well, then I shall. Thank you very much, Davidas. Right. Let's see. Can you see my screen?
Yes.
Lovely. Also, if there's some noise from the outside, interrupt me and let me know. I shall close the window then. But without further ado then, hello everybody. Like David has mentioned, I'm Donatas. And today I'd like to cover the topic of speech recognition for small languages, the TLDR version. And well, now a little bit about me. I am the CTO and co-founder at Oxus AI, like David has mentioned. And Oxus AI is a startup working on rapid and objective feedback for speech workers. Speech workers are people who work, for example, in sales calls or in call centers and who answer calls. And we want to provide better analysis with speech technology. Now, this is already kind of solved in English and similar well-resourced languages. However, it's not solved in many languages that are smaller or that have less resources. And that's what we're trying to do. And the basis of my presentation comes from the knowledge that I acquired whilst trying to solve this problem. And additionally, we're also hiring at Oxus AI. So if you know anybody who would be interested in democratizing access to speech analysis, be sure to let them know about this. Now, with the shameless plug out of the way, let's move on to the plan. And the plan is pretty simple. I'd like to simply cover the problem that exists with languages and speech recognition in them, and to cover a few methods how it is possible, how at least currently the industry is solving them. And let's begin with languages. I'd like to ask a simple question for the start. And the question is, how many languages do you think are there in the world? Are there hundreds or thousands? And because I can't receive your answers, unfortunately, I'll have to assume that you all got it wrong. And the actual answer is around 7,000 languages. And for me, that number is very impressive because when you think about it, there's only around 200 officially recognized countries in the world. That means the amount of languages is by far a different order of magnitude number. And there's a different dynamic that comes with languages. It's that they have a very large tail. If we look at this graph, you can see that the largest language by the number of speakers is Chinese Mandarin, as expected. And then the languages tamper off. And if we only take around 25 of the largest base languages, we already cover more than 50% of the languages, which means that the other 7,000 languages all cluster in the rest 50%. All of them are very small. And this is a problem in machine learning. As if anybody has ever tried machine learning, you might have heard that data is important. And with small languages, with small speakers, data becomes a very big problem. So very few speakers means that there's little incentive and little data being created for these languages. Now, the situation is not as dire as it used to be because there are tools like, for example, Mozilla Common Voice, which allow crowdsource intelligence to create data sets for these languages. The way this tool works is very simple. People just log into the tool, they select the language that they can speak. One of the low resource languages, for example, here's the Lithuanian, and they either record the speech or listen if others recorded the speech correctly. And this is how a transcribed data set is created. However, even with tools like these, the problem still persists. Here we can see a comparison of the same tool, the Common Voice tool, but the differences in its data set sizes. We can see the comparison between English, Catalan, and Dutch. And we can see that the language disparities quickly arise here too, with Dutch barely even noticeable compared to English data set size. If anybody's interested, by the way, Lithuanian sits at 420 megabytes for some reason, and it is around 4 times, even a little bit more than 4 times less than Dutch. If you remember, Dutch already wasn't doing so great. The QR code over here, by the way, is for people who want to go into the tool and later improve the situation by actually labeling the data themselves. Now, I believe there's one more thing that's important to mention, is that there's a lot of push from universities and from governments, from institutions to improve the situation. And in some cases, it's actually working pretty well. For example, in Lithuanian language, we have a project called Liepa, which is creating a large transcribed data set. However, it's not something that we can trust all of the 7,000 languages will have, because not all of them are well funded and not all of them are main languages of the countries. So they are not necessarily even supported by the countries. So if we know now that the data situation won't improve, the only other option is to actually use less data, to use less labeled data. And there are a few approaches that actually work here, but I'd like to mainly cover two. The first one is actually looking at the problem from a bit of a different perspective. And it's a limited dictionary approach. Basically, so far, what I've been talking about has been speech to text. What I've been talking with most in my mind has been speech to text approaches. That's if you imagine YouTube, when you turn on closed captions and it tells you everything that's happening in the text. But there's a different beast of speech analysis, and that's keyword detection. This is more akin to if you imagine saying, hey, Google to your phone, and when it reacts, or Siri, if you're that type of person. That's called wake word detection. And these models are much smaller, and they detect only a limited dictionary of words. So different models can be trained, for example, with 100 words of detection. And this, in turn, requires orders of magnitude less data, which is great for small languages. However, you probably at some points want to have the full transcription to do more analysis. Or for example, if you want to provide closed captions on videos, you also need full transcription. So this model doesn't solve all of the problems. A different solution would be to use unsupervised and self-supervised learning. So this is very similar to what, in essence, to what was just described in the presentation before me by Julius, but a bit of a different take on it. And I'd like to cover two models on this side because they're both related. And in order to talk about state of the art, we first have to cover VAF2VEC 2.0, which came out about a year ago and was a very interesting approach to speech recognition. Now, I won't cover the basic working principles of VAF2VEC 2.0 right now. If people are more interested, you can ask me in the Q&A. If you know how Words2VEC works, it is a very similar method of training, but the purpose of this model is basically to take a snippet of audio and convert it into a vector. So a representation of digits, a list of numbers that have the semantic meaning of this snippet of audio. So in the Word2Vec case, these numbers, for example, explained how manly something is, or how a feature that says how royal the word is. In audio space, they're different, but they still exist. And this model actually worked incredibly well for what it was. Here we can see a clustering of the results after this model was trained, the VAF2VEC model. And we can see it clustering similar languages together in clusters, even though it knows nothing about the semantic tree structure of these languages. It knows nothing about that these languages are similar, but it clusters them because it has learned this. It wasn't given this information beforehand. Now, this model, by the end, it doesn't give transcriptions. That's not what it gives. It gives a vector of numbers. So there's still some labeled data required to make this actually work. And that's where this model isn't perfect for small language recognition. However, it improves it dramatically. After applying an additional model on this VAF2VEC model to actually make transcriptions, Facebook was able to get these results. And these are seriously impressive. Here you can see on the left the word error rate that was achieved. Word error rate simply means that if we take the transcription of 100 words, how many of those words were wrong in the transcription. And we see the models used here on the bottom. The amount of hours means how many labeled or transcribed hours of data was the model used. We're using to train the model. And if we look over here, a special version of VAF2VEC model with 10 minutes of labeled data achieved 8.6 word error rate. And this is a seriously impressive result, considering that the human word error rate of transcribing speech is 4%. This line, kind of eyeballed it, is around 4%, representing the human level. So that is seriously impressive, however, not human level yet, and also still requires labeled data. Well, that's where a new model from Facebook comes in. And this is high-performance speech recognition with no supervision at all, which means not even the 10 minutes of labeled data are required to create transcriptions. And to explain how this works, I will try to go through the process. If I'm not clear, you can again ask more in the Q&A session. The whole working principle can be segmented into two parts. And the first part, the top part over in the image, is very similar to what we were talking about, the vanilla WAF2VEC model. And here, the same process happens. We have unlabeled speech audio being vectorized by WAF2VEC models, so turned into numbers. And then we have some additional fancy techniques to tell how to segment this audio, but we can ignore this for now. The idea doesn't change. So at the end, again, we have audio snippets that have been turned into numbers. The interesting part is the second part. So previously, we were using these numbers and we were using actual labeled transcriptions of the same audio to tell the model how it should transcribe. Now, we don't have the labeled data. What we have instead is a GAN model, a generative adversarial network, and random unlabeled text. This is just random text of the same language. So if we imagine Lithuanian language, this could be just the constitution or the Wikipedia entries in Lithuanian language. Preferably something like speech data, but the idea is still the same. And what we have then, we have a generator that simply receives the same numbers, the numbers from the unlabeled speech audio, which in themselves hold information, but they're not transcriptions yet. And it is supposed to produce the transcriptions out of itself. And we have a discriminator that is supposed to tell the difference between actual transcriptions, so actual labeled text of this language, like we can see here, and the predictions by the generative adversarial network, which at the start are complete nonsense. But with time, these become actual transcriptions. Now there's a video that better illustrates this process, and I think I can show it here. So like I mentioned before, we have a generator model that receives the vectors, so the numbers representing what's happening in an audio snippet, and then it produces an output. At start, completely random output. And we have a discriminator on the right, which is supposed to tell the difference between real and fake recordings, real and fake text. In this case, it's probably pretty easy for us, and it should be pretty easy for the discriminator. But the discriminator constantly learns how to tell the differences between real text and fake text because it gets examples of real text. Because of the feedback loop that comes back to the generator, it constantly has to improve its predictions so that they look more and more like real text. And eventually, this ends up with a generator that is able to provide very accurate transcriptions. How accurate? Very. So here's a WAF2VEC model. WAF2VEC-U stands for unsupervised. This is precisely what I was just talking about. And the model that was trained on 0 hours of transcriptions, so none at all, is performing at around 6% word error rate. All these models on the left, right here, have used at least 960 hours of transcribed data, even more, some of them. So the improvement is very significant, and this is very exciting for small languages. Now, by no accounts is it perfect, because this is still English language. The result here is on English language. Even though it didn't use any labeled data, there's still vast amounts of data to train, and there's a lot of analysis that's been done before. On other languages like Swahili, it's still performing worse. If I remember correctly, the accuracy is around 13 or 12%. And there's a different problem that actually comes up with these types of models, and that's that for some languages, for small languages, even the amount of unlabeled data starts to be a limiting factor. For smaller languages, even just getting the recordings of this language without saying what's in there, just the recordings, might not be enough in the amounts of hours that exist there to train such models. So there's still a lot to improve, but the field of speech recognition, especially for small languages, has been accelerating and has been a very interesting to follow. And I hope I was able to introduce you to it, the TLDR version. And if you have any questions, I'd be more than glad to answer.
Yeah, thank you very much, Donatas. Very interesting topic. So maybe I just check the YouTube if we have any questions. I think we don't have any questions. So maybe if you have some question, you can write in the comments, and after that, sometimes maybe Donatas can answer, because we also don't have Julius. He should go. So yeah. So maybe if you have any question, you can answer, or you can ask on comments, and after the meeting, I think Donatas could answer them. Yeah. So thank you very much for everyone who's participated, for all the speakers, for you, Donatas, for Julius, for Dovydas, and see you on October, our next meetup. Yeah. So thank you very much, and have a good evening.
Thank you. You too.